All right, ensemble learning. So what is ensemble learning? It is to generate a set of many diverse learners and combine the results to improve over a single learner, right? That's the idea, basically putting together different models, and so at the end we take their combined effect as a final solution. All right, so generally there is two main different ensemble models. One is bagging, the other is boosting. Bagging reduces the complexity of the models, they increase the bias, right? So remember, if a model is too complex, it has high variance and low bias, right? When you combine the models together, it will increase the bias and lower the variance a bit. So that's bagging there. Now, some other models have low variance and high bias. So there we want to increase the variance and lower the bias a bit. So that's where we apply boosting. When you say combine, how do we do this? Max voting is one idea, right? So each base model, the base model means each of the individual models used in the ensemble model will make a prediction and have a vote at the end. Okay, so generally there's some model methods listed here, but it's generally the majority rule. So the one, let's say if this classification, one predicted class that has the largest number of votes will be the winner, and that will be the final prediction class for the ensemble model. Now, when that voting is done, there's hard versus soft voting. So what is hard voting? It is the basically each model makes a prediction, the class label, right? And then the average is taken at the end. Okay, so that's hard voting. So if there's classes 0 and 1, let's say class 0 got 4 votes and class 0 got 6 votes, well, class 1 is the winner, that's it. The soft voting looks at the probability, so not the class labels directly like this, but rather probability. So the first model in the ensemble, let's say this model, predicted a prediction of, so if there's two classes, right, the probability will range between 0 and 1. So let's say its prediction probability is 0.65. So these are the probabilities that class, that the label is class 1. So the second will predict a class probability for class 1 to be 0.05 maybe, the other one 0.69, and the final, let's say 0.42. Okay, so what happens in the end? So these are the probabilities for class 1, right? So we add them up and we take the average. Okay, so that will be the probability of being class 1. Now 1 minus these values will be the probability for class 0. So we do that as well. So we take the average of those votes, and then that will be the class, the probability of being class 0. Okay, and then the one that has the larger probability will basically be the winner. Okay. So that's how it is done. So it's called soft voting because rather than taking the exact class labels, it's working on the probability. So it's a bit more fine-tuned, if you will. So averaging is usually used for regression problems. Okay, so or it is used when the when we take into account probabilities in classification, right? Like we did. So so if it is a regression problem, it will be a continuous value being predicted from the different learners, and then at the end the average is taken, right? So weighted average can also be used in a similar idea, where rather than treating each model's prediction the same with the same weight, maybe some models can be given more weight. All right. What are some of the advantages? So generally the goal here when we combine the models is to reach better solutions than the individual models themselves, right? So they will perform much better than their weak learners in general. Ensemble models can reduce the bias or variance in a different based on their application. So they're non-parametric and don't assume the data to follow a particular distribution. This mainly stems from the fact that the ensemble models are generally to be tree-based models. So in general, decision trees are used as their components. So that's why, basically the same ideas apply here as well. That applies for the decision tree. So they don't assume any distribution and they're non-parametric. Then they're in scale invariant as well, again, something from decision trees. The features, there might be issues with being the features highly correlated with each other, what we refer to as multicollinearity. That's all right, as long as we are mostly concerned with the performance of the model rather than the interpretation of the model. Meaning, if you want to define the variable importance, like understand which variables are contributing more to the solution and those kind of things, then that can be a problem. But if that's not so much of an issue for us, if you're just more interested in having a high performing model, then the ensemble models are generally good. The ensemble models are generally robust against outliers and noise, so that's another good advantage of it. And in some other complex models like SVM and neural networks comparatively are more require more computation. So the ensemble models are computationally more efficient compared to them. Bagging stands for Bootstrap aggregation. Okay, so the word bagging, it's not really about bag. It's the short for Bootstrap aggregation. Aggregating equally, so here we aggregate equally the results of the weak learners built independently on random samples to create a strong learner. So random samples are taken, models are built on them, and then the final results are combined together. Okay. So it's generally good when you have a high variance problem. So like decision trees, right? Decision trees are known, at least if you allow them to fully grow, they are, they will overfit, they will have high variance, and they will have low bias. So that's why bagging is a good way to combine them together to get a better solution rather than an individual decision tree. And since the decision trees are really dependent on the data, so a small change in the data will lead to a very different decision tree. So that means they are highly unreliable and unstable. When you combine the decision trees trained on the different bootstraps, right, or random samples, then basically, and then taking the average, kind of helps us reach a better, more reliable, more stable solution, right? And since each tree is trained on a different random subset of the data, they can be basically grown or they can be trained at the same time. That means they are parallelizable as well. So the general outline of the bagging algorithm is we do bootstrapping, right? And then we create those bootstraps. And then we build models on them. So we have model C1, C2, CK, and so on until we have K models basically. And each model is distinct, right? Why are they distinct? Because each model is trained on a different subset of the data. So these Z1, Z2, and so on are different from each other. They are bootstraps from the original data, so there is differences between them. So the models will also be different. Okay, so the same models are trained. So what that means is that if we can basically try different base models here. It's not a must to always have this in trees. We can use some other more simpler models as well. However, mostly, again, as I said, decision trees are preferred in ensemble models. So if you decide on decision trees, each of the models here is a decision tree. Okay, so this is decision tree 1, decision tree 2, decision tree 3, and so on. So each of them will be a decision tree. So that's what it means to be homogeneous. Okay, so this can't be a decision tree and then a logistic regression and then I don't know, an SVM or something. That doesn't work. Each model has to be of the same type. But again, because they were trained on different subsets of data, each model will look different, right? In this case, decision trees will look different. And at the end, we can make predictions. So for classification, we take the majority vote. The class that takes the largest number of votes wins. For regression, we take the, each of these trees will predict a numeric continuous value. So we take the average of those values. So that's for regression. What is out of bag? If you remember, when we started talking about bootstrapping, we mentioned when we create the bootstraps, they are of equal size to the initial data set, and random sampling with replacement is done, right? And then so we were creating data sets like this, right? But some of the data points were never selected in these subsets. So these subsets that were not selected, these data points, is called OOB. They are out of bag. So they were not put into this bag. If you assume this to be a bag here, they are outside of the bag. So these OOB data sets can be used as a pseudo validation or a pseudo test set. All right. So that's the main goal here. So, the idea of validation cross validation, this is another idea that can be applied when you use a bagging algorithm. Because of the bootstrap creation, the points that are not selected can be treated as a test set. And instead of doing cross-validation or validation, this can be used for training and this can be used for validation. That's a good point of out of bag, or using bagging basically. Approximately about 1/3 of the data points will not be selected. So this out of bag will be around 1/3 of the whole data set. Okay, so the calculation is shown here. There's, the way we reach this solution is shown here as well. So the performance of each model on its left out samples when averaged can provide an estimated accuracy of the bagged models, right? So this estimated performance is called the OOB estimate of the model performance. These performance measures are reliable test error estimates and correlate well with cross-validation estimates as well. Bagging, the bias and variance. So it's good to apply when each single classifier is unstable. They have high variance, like decision trees. Unstable, meaning, again, even a slight change in the data will lead to very different decision trees, so it's unstable. Aggregated classifier will have smaller variance than a single original classifier. It is found that the bagging reduces variance, right, without significantly increasing the bias. So normally, remember, it's important that there's always a balance between bias and variance. When the variance goes down, the bias goes up. When the bias goes down, the variance goes up. But again, if you can manage to reduce the variance without increasing the bias too much, then basically we are doing a better job in terms of reducing the overall error, and that's achieved by applying the bagging algorithm. So again, that's a good advantage of using the bagging models. And that's it. Thank you so much.